As we have already discussed before, we will focus our discussion more on dynamic systems. When we are dealing with a static system, as I have already mentioned also before, the relationship between input and output is normally represented by algebraic equation, by just summation, multiplication, subtraction, or division. It's just a simple algebraic expression. So it's pretty easy to find the output if you know the input for a static system. In the case of dynamic system, the relationship between output and input is represented by differential equation. The question now, how to evaluate output of a dynamic system for any given input, since the relationship is given in differential equation. So this is a thing that we are going to discuss in this topic, how to evaluate an output of a dynamic system for any given input. One among many tools that we normally use to solve a differential equation problem is a Laplace transform. I believe you have learned about this Laplace transform before when you were studying MA 2006 Advanced Engineering Mathematics. So we will revisit this briefly on how to use Laplace transform. In the following next few slides, we will briefly discuss on the definition of the Laplace transform. Again, I will not discuss to detail. If you want to refresh again your memory on Laplace transform, I strongly advise you to refer to your MA 2006. So after we discuss the definition, later on we will discuss some basic transformation of Laplace. I will also discuss some properties of Laplace transform, and then in particular I will discuss two main important properties of Laplace transform, which are final value and initial value theorems. Okay, the first question perhaps, why do we have to use Laplace transform? As I mentioned many times, the relationship between input and output in dynamic system is represented by differential equation. Solving differential equation is not easy. It's not as straightforward as solving an algebraic equation. Laplace transform will help us in solving this differential equation. How does it do? We will transform the differential equation into a form of algebraic expression. Once you have an algebraic expression, you can solve the equation relatively easy. So you can have the solution by using this Laplace transform. So basically Laplace transform will convert any ordinary linear differential equation into algebraic expression to simplify the problem so we can solve it easily. Let's take an illustration. Let's consider a simplest differential equation ever. So let's imagine here you have an equation. You want to solve the xt function of x here, in which in here you know that the first derivative of your x is equal to 2 times t. T represents time. If you want to find the solution of this problem, you want to find the xt, it's very simple. You can just simply integrate the 2t. So you just integrate 2t, you will end up into xt equal to t squared plus a constant. So you solve this simplest differential equation. Let's move into a second example. This is slightly more complex, but it's still easy actually if you remember how you did it in MA 2006. In this case, you have an equation, differential equation, in which the solution that you are looking for, the xt, does not appear only by itself on the equation, but the equation involves also the first derivative of x. the first derivative of the solution that you are looking for. The first derivative of x plus x itself is equal to constant. That is what the problem says. And then we want to find the solution of xt. So this is slightly more complex than the first one, but with the help of exponential expression in the solution, you can easily find that xt is equal to a constant a times exponential of minus t plus another constant c. You can solve this relatively easy by owing to the exponential expression in the solution. So you still can solve this easily without the help of Laplace transform. But let's take the third example here. This is much more complex. If you look at this, the problem here, we want to find the solution of xt, but the equation here involves not only the first derivative of x, but also the second derivative of x, where in this equation you can see alpha and beta, both of them are constant, and this equation that involves the first and second derivatives of x of the solution that we are looking for is equal to function of t. You want to find the solution of xt. This is not easy. This is definitely not easy. You cannot solve it in straightforward manner. So how to solve this problem? We are using the Laplace transform tool. So if you look at this diagram, we have a problem. We have a differential equation in our case here. Looking at the previous slide, so we have this problem that we want to solve, and then we want to find the solution xt. In the previous two examples, we can solve it relatively easy. We can just solve it directly from the differential equation, and then we can find the solution xt. In the last example, to find the final solution, to find the xt is not easy at all. So what we are going to do, Laplace transform will convert our differential equation, the problem that we want to solve, into another form. We will convert it into another domain, where initially the domain is in time. The Laplace transform will convert the differential equation into another form in the domain of Laplace. But after we convert it to this domain, to the Laplace domain, the differential equation that looks pretty complex will appear into a simpler expression, which is expressed by an algebraic equation. So now we have an algebraic equation to solve. Algebraic equation is always easy to solve. It only involves plus, minus, summation, subtraction, multiplication, and division. So we can easily solve this algebraic equation, and then we can have the solution of this problem. But again, the solution that we have here is still in Laplace domain, in a domain of S. S represents the Laplace. This is not the solution that we are looking for. So what we have to do, we use again the Laplace transform to transform the solution which is currently in Laplace domain to the time domain. And then we can find the final solution that we are looking for. So this is the concept of Laplace transform. It takes a longer route to find the solution, but the route is smoother. You can solve it easily because you have a simple expression now. Up to this point, you might have a question then on how to transform the problem from time domain to Laplace domain. Afterward, after we find the solution, how to transform it back to time domain to find the final solution. You might have that kind of question. So if you look at this slide, I will show you two equations here to transform an equation from time domain to Laplace domain and vice versa. So the first equation here is the equation that we use to transform time domain expression to Laplace domain. Let's say we have a function ft and then we want to express it in Laplace domain. We want to convert the time domain expression ft to Laplace domain. So we are going to convert ft to a function in Laplace domain fs. How to do that? You just simply use this formula. You multiply ft, the time domain function that you want to convert, by exponential of minus st, and then you integrate it with dt. You integrate it from negative infinity to positive infinity. After you integrate it, you will get a new function fs, a function in Laplace domain. That is the converted time domain function ft in Laplace domain. And then after that, after you get the expression of the function in Laplace domain, you can solve the problem easily, because after you convert it, I guarantee you will get an algebraic expression. You can solve it, you can have the solution, but the solution is still in Laplace domain. So after that, you have to convert the solution, which is currently in Laplace domain, back to the time domain. How to do that? You use the second equation. So how to do that? If you have the solution in Laplace domain, let's call it fs, you want to convert it to function in time, you just simply multiply the solution, which is in Laplace domain, by exponential of st. You integrate it with respect to s, the Laplace domain, and then you evaluate it from c minus j omega to c plus j omega. J denote the imaginary value, and then you multiply it by 1 over 2 pi j. At this point, you will get the time domain counterpart of the Laplace domain function. So by using these two formulas, you will be able to convert the function from time domain to Laplace domain and convert the solution back from Laplace domain to time domain. But at this point, it doesn't make sense again to me. I'm taking a longer route to find a solution easier. But I expect by taking a longer route, the solution will be simpler. But I have another problem here. Converting a function from time domain to Laplace domain and vice versa for the solution, it doesn't look simple. I have to evaluate this complex operation. I don't like this kind of integration. I have to integrate it for an infinite value, and then I have also, in this case, I have to integrate it with a complex number. This is not an easy way to calculate. So I'm willing to take a longer route to make my life easier, but I introduce a complex problem here when I try to convert the function from time domain to Laplace domain and vice versa. This doesn't make sense. This doesn't make my life simpler. But luckily, fortunately, converting a function from time domain to Laplace domain and vice versa, you don't have to use that complex equation, that complex formula. You can simply refer to a table, Laplace table. So by referring to this Laplace table, you can convert any equation, any differential equation in time domain to Laplace domain. And once you find the solution in Laplace domain, again, you just simply have to refer to the table, and then you can convert it to time domain. So this way, you really make your life much easier.